Okay, this video is on stoichiometry. Then we're going to go to limiting reactant and finish it up with theoretical yield and percent yield. So the first part, we just look at the balanced chemical equation, and we want to know if we have a certain amount of some starting material, you know, how much product can be made, or how much how much of the other reactant do we need, things like that. So here we find that there's a ratio between the coefficients in the balanced chemical equation and the moles. So the coefficients and the moles are proportional. And we can just kind of eyeball some of these questions here and figure out what the answers are. But before we start, the reaction is, this one is tin 4 oxide, and it's in the solid phase. Then you have 2 carbons in the solid phase. There's 2 phases. Actually, there's more, but we'll talk about 2 phases of carbon. One is graphite, and the other one is diamond. So thermodynamically, the graphite is the more stable form. That's not indicated by the word solid here, but we'll assume it's not diamond. All right, and then it's going to form tin, and this little thing that looks like a 1 is actually a lowercase l for liquid phase. When you type it, it looks like a 1 or an I, capital I. So watch for that. And then carbon monoxide in the gas phase. All right, so here are the questions. I'm going to spread them out and see if I can write in between them, because they're simple enough. And I'll put it in blue. So how many moles of carbon monoxide can be made from 1.2 moles of tin 4 oxide? So you want to look at the balanced chemical equation. You see that there is a 1 to 2 relationship. Should just point with that. Sorry. A 1 to 2 relationship between them. So how much CO can be made from 1.2 moles of this? If you have 1.2 moles of this, then you're going to be able to make 2.4 moles of that. That's the idea. But then you want to use the factor label method, or the dimensional analysis method. You start with what you have, 1.2 moles tin 4 oxide, and then you take the ratio of the coefficients in the balanced chemical equation. So you want to say that there are 2 moles of carbon monoxide for every 1 mole of tin 4 oxide, and that'll give you the 2.4 moles of CO. So this is a way to do it with the units canceling out that you don't need, and you end up with the units that you want, which are moles of carbon monoxide. All right, for the second one, how many moles of tin can be made from 13 moles of carbon? Let's see, we have 13 moles of carbon. How many moles of tin can be made? So you can see the tin is half the value of the carbon. So this is going to end up being divided by 2 to give you the moles of tin. So it should turn out to be 6.5. All right, so let's do it systematically here. Write down your 13 moles of carbon. Then you look at the coefficients in the balanced chemical equation, and you say there's 1 mole of tin for every 2 moles of carbon, and so this is going to be 6.5 moles of tin, and your moles of carbon are going to cancel out. All right, and then let's see the third one. How many grams of tin 4 oxide is needed to completely react with 14.4 grams of carbon? Now in this problem, you have to go from grams to moles for the carbon, and then you look at the mole relationship with regard to the coefficients. So we're going to use 12.01 grams per mole to convert this to moles, and then we're looking at the relationship between the carbon and the tin 4 oxide. So given a certain amount of carbon, how much tin 4 oxide is needed? Okay, so this one, 14.4 grams of carbon, use molar mass 12.011 grams per mole of carbon. Then use the coefficients in the balanced equation, 1 mole of tin 4 oxide for every 2 moles of carbon. The question is how many grams. You need the molar mass of tin 4 oxide. It's 150.7 grams tin 4 oxide for every 1 mole tin 4 oxide. So if we did it right, let's see, grams cancel, carbon, moles carbon cancel, moles tin 4 oxide cancel, and then we're going to end up with our answer, which is 90.3 grams of tin 4 oxide. Okay, so we went grams to moles to the ratio of the coefficients, and that back to moles, and then to grams. Okay, similarly, how many grams of tin can be made from 13 grams of carbon? So you're going to have grams of carbon, you got to go to moles of carbon, then you're going to go from moles of carbon to moles of tin, so it's a 2-to-1 ratio here. Once you get your moles of tin, then you're going to go back to grams. Okay. So for this one, start with what you have, 13 grams of carbon, and use 12.011 grams of carbon per mole of carbon. Then you want to say that there are 2 moles of carbon for every 1 mole of tin. And then you want to go to grams of tin. The tin is 118.71 grams per mole. And so this one turns out to be 64.2 grams of tin. Let's just check our units. Grams of carbon cancel, moles of carbon cancel, moles of tin cancel, and we end up with grams of tin. All right, the next problem here is our limiting reactant problem. And this problem is something that you've probably seen in high school or some other chemistry course that you might have taken. And I always start out simple with a kitchen example. Textbooks tend to do that too, with making sandwiches. How much bread versus how much, meat you have, for example, in your sandwich. So the reason is just to kind of get you thinking along the right lines, how to think about the limiting reactant problem, and then we'll switch to molecules and masses of certain reactants, limiting reactants, and so on. All right, so in the case of the limiting reactant problem with the lemonade, here's our recipe. The recipe is like the balanced chemical equation. In this case, 6 lemons plus 1 cup of sugar makes a quart of lemonade when you add the water. If we have 12 lemons and 3 cups of sugar, how many quarts of lemonade can be made? And if you think about it, your normal thinking is to say, okay, if I have 12 lemons in the kitchen and it's a 6-to-1 ratio for the recipe, then I would need to have, if I have 12 lemons, I would need 2 cups of sugar. So 12 to 2 would be the same as 6-to-1. And if that's the case, then I'm going to have some extra sugar. I'll have a cup of sugar left over. On the other hand, if I look at my 3 cups of sugar, I might say, how many lemons do I need? And since it's a 6-to-1 ratio, you're going to need 18 lemons to use up all 3 cups of sugar. And if you're doing it by 3, then this will make 3 quarts of lemonade. So, which is correct, and the answer is the lemons. Given what you have, you don't have 18 lemons here, so the lemons are going to be your limiting reactant. The lemons are the limiting reactant. They determine how much product or how much lemonade, in this case, is going to be made. All right, so I'd like to just kind of write things out here in some detail. And you can just bear with me on this. Maybe you're bored already, but that's okay. So let's just talk about normal thinking, which is what I just went through there. And with normal thinking, all right, I'm in the kitchen. I got 12 lemons. My recipe says 6 lemons for every 1 cup of sugar. And that's telling me I need 2 cups of sugar. So I have enough sugar. Therefore, the lemons limit the amount of lemonade that will be made. On the other hand, if I look at 3 cups of sugar and my recipe is 6 lemons for 1 cup of sugar, this is telling me I need 18 lemons. Okay? And so I don't have enough lemons to use up all the sugar. Okay, combine that information. You're going to come up with the idea that the lemons are the limiting ingredient or the limiting reactant. All right, so now if I want to know how much lemonade I can make given 12 lemons and 3 cups of sugar, you want to use your limiting reactant or limiting ingredient, which is the lemons. So you say 12 lemons, and you want to convert that to how much lemonade. The recipe says 1 quart of lemonade for every 6 lemons, and that's going to be 2 quarts lemonade that can be made. All right, we're going to have a cup of sugar left over, but let's wait. I'm going to talk about something else first. So this is your normal thinking when you're in the kitchen, and this is why we do the kitchen example, because this is exactly the way you want to look at it. I'll just put here 1 cup sugar left over, and I'll show you how to calculate that next. Okay, but this is not the method that we're going to use. This is the way it used to be taught in the old chemistry books, but now they use a different method. So book method. The book method is to take each one of the ingredients, 3 cups of sugar, calculate how much lemonade can be made. And that is 3. All right, take your other ingredient, 12 lemons, and 1 quart of lemonade is in the recipe. You need 6 lemons to do that. So you get 2 quarts of lemonade. So you've calculated the amount of product or the amount of, in this case, the lemonade. You've calculated it twice. Look at what you've done here. So you got the 2 ingredients. This ingredient produces this much lemonade. This ingredient produces this much lemonade. So in other words, if sugar was the limiting reactant, you could make 3. If lemons were the limiting reactant, you could make 2, and you're going to pick the smaller number. So the book method is take your reactants, calculate the same product twice, in this case it's lemonade, and pick the smaller one, like that. So this one is the correct answer. That's the method we're going to use. Now, I didn't finish it on the last example there, but you know, we got to calculate how much sugar is going to be left over. So how much of the, so this would be part B, how much of the excess reactant or the excess ingredient is left over? The word is ingredient, is left over. And the technique is to use the limiting reactant. The correct answer here is the limiting, no, I'm sorry. The correct answer up here is that you're going to make 2 quarts of lemonade. That makes the lemons the limiting reactant. Let me put that in red. I usually put an arrow back over here and say limiting reactant. So once you figure out what the limiting reactant is, you're going to use it for all your other calculations. In this case, it's just one. We want to know about the sugar. So you're going to use your lemonade now, 12 lemons. Use your limiting reactant, and you have to go back to your recipe, which is 1 cup of sugar is used up for every 6 lemons. So it's going to take 2 cups of sugar to make the 2 quarts of lemonade. So this is the amount that's used up or consumed. And then how much is left over? You started with 3 cups of sugar minus 2 cups of sugar. You're going to have 1 cup of sugar left over. So this is your initial amount of sugar. This is the amount used up. And then this is the amount that's left over, 1 cup of sugar right there. All right, so then that's the method. I'll just get a new page for that to use. But before we do that, let's look at just, this is going to be molecules A, B, C, and D. And just use your, use the numbers and the ratios. You could probably have a look at this and figure it out. So if I have 5 moles of A and 2 moles of B, how many moles of C and D can I make? Just focus on C here. So it's a 2-to-1 ratio. If I have 2 moles of B, then I'm going to need 4 moles of A. That's going to make B the limiting reactant, and there's going to be 1 mole of A left over, right? And then if since it's 1-to-1 and you have 2, you'll end up with 2 moles of C. It's 1-to-1 here, so 2 moles of D as well. How many moles of excess reactant will be left over? You have 5. You're going to use up 4, so you're going to have 1 left over for that one. So the answer here, just looking at it, is that B is the limiting reactant. And you have 2 moles of it, so you can make 2 moles C and 2 moles D, and there will be 1 mole of A left over. So if it's just, you know, some simple numbers, simple ratios, you can do it in your head. There's not a problem with that. Also, let's see, we've accounted for A, C, and D. How much B is there? The answer is 0 at the end of the reaction. So B, the limiting reactant, is completely consumed. All right, this one's a little bit more complicated. The ratios are not so obvious in your head, perhaps. So you have 6 moles of A and 7 moles of B. How many moles of C and D can be formed? Actually, you probably could do this in your head, but let's go ahead and write it out because I want to emphasize the method here. All right, so for part A, we want to know how many moles of C and D can be formed. What we want to do is calculate C first, and then we're going to do it twice. The first time using A, the second time using B, and then we're going to pick the smaller number. Once we got C, then once we know the limiting reactant, then we can figure out the D. All right, so this is the book method. So we're going to calculate C twice, and we're going to start with 3 moles of A. The ratio is 6 moles of C for every 3 moles of A. Those are the coefficients. And so this is going to be equal to 6 times 2 is 12 moles of C. Then we're going to calculate C again from our other ingredients here, 7 moles of B. And we're going to calculate C, so 6 moles of C for every 4 moles of B. And this one is going to be 10.5 moles of C. So we're going to pick the smaller number. This is the correct amount formed. And B is the limiting reactant. So this is the correct amount of C formed, 10.5. You pick the smaller number, and then you'll know which one is the limiting reactant as well. So then if the limiting reactant is B, then B is completely consumed. You're going to have some leftover A. So you get 0 moles of B at the end, but then you'll have some leftover A. So part B here is to, let's do it back in red, I suppose. B, let's do it in black actually. B would be to use the limiting reactant to figure out, to get leftover amount of A. Okay, so we're going to use limiting reactant, which is 7 moles of B. That's how much we have. And then we're going to calculate, we're going to use the 3 to 4 ratio here. So every 4 moles of B consumed, 3 moles of A are going to be consumed. So 3 moles of A for every 4 moles of B consumed, 21 over 4, and that one, oh, I forgot to calculate D, sorry, I was looking at the wrong one. So it's 3/4, yes, this is going to be 5.25 moles of A consumed. All right, and then you started with 6 moles initial. So 6 moles of A initial minus 5.25 moles of A consumed or used up in the reaction. And then the difference is 0.75 moles of A left over. Okay, and we got to go back and get D. D will be equal to the same as, will it? No, the ratios are different here. Yeah, 6C and 2D in D. Let me show it to you here. So how, let me do that. How much D will be formed. So we want to use our limiting reactant B again, and we're going to calculate the moles of D that will be formed. Use the limiting reactant in this case. So B is limiting reactant. We have 7 moles of B, And the ratio is 2 moles of D for every 4 moles of B. So you get 3.5 moles of D formed. Okay, we can summarize and make a table here. So the reaction was 3A plus 4B forms 6C and 2D. And you can look at what the moles were before the reaction and what the moles are after the reaction. Just kind of tabulate it. Make sure it all makes sense here. So you have 6 moles of A and 7 moles of B to start with. You have 0 moles of C and 0 moles of D to start with. Then the reaction takes place. You have 0.75 moles of A left over. The limiting reactant is completely consumed. 10.5 moles of C are formed, and then 3.5 moles of D, we just calculated that part, are formed. And you can try adding these up just to kind of make an observation here. So before the reaction, you have a total of 13 moles. After the reaction, you have 14.75 moles. Is that right? 0.75, 10. Yeah, okay. So you do not have conservation of moles. The moles before do not equal the moles after. So no conservation of moles. On the other hand, there is such a thing as conservation of mass. I'm going to show you that in the next problem. All right, so here we go. These are the hard ones, and how many of these do I have? Let's this one, and then I got another one coming up afterwards. Okay, so here we go. You got masses that have to be converted to moles. Use your coefficient ratio to get moles of whatever you want, product, and for example, then you got to go back to grams. So grams to moles, moles to moles, moles to grams would be the process here. So in this reaction, you have 1.93 grams of C2H4, 5.92 grams of O2, and you want to know how much CO2 and water, and then how much left over of the excess reactant remains. So first of all, how do you know that you have a limiting reactant problem? And the answer is you have quantities of more than one reactant. You've got quantity of this and you've got quantity of that. Which one is going to determine how much product is going to be formed? So that's how you recognize it. You have quantities of both of these things. All right, so we're going to use our method here, our book method, which is to take the grams of C2H4. Let's just start with the CO2, calculate the amount of CO2 formed. Then you're going to take the grams of the O2, and we're going to go back and calculate CO2 again. And then we'll compare the quantities of CO2. We'll pick the smaller one. That will be the amount formed, and then we can go back and figure out which one of these it came from, which one of these the smaller CO2 value came from, and that'll be the limiting reactant. Okay? All right, so let me just move this up. I guess I'll put it on another piece. Another page here. Okay, so we've got, I'll write down the reaction. C2H4 plus 3O2 forms 2CO2 plus 2H2O. And we have 1.93 grams of C2H4, 5.92 grams of O2. And let's go ahead and get the CO2 in two separate calculations here. So for the C2H4, you're going to say 1.93 grams. And the molar mass of that compound, 28.08 grams per mole. All right, we're going to go to CO2. So it's going to be 2 moles of CO2 for every 1 mole of C2H4. Then we have our CO2. And now we're going to go to grams, so you use 44.01 grams CO2 for every 1 mole of CO2. That's the molar mass. So this one turns out to be 6.05 grams of CO2. Okay. Then 5.92 grams of O2. Use diatomic molecule molar mass, so it's 16 times 2 is 32 grams of O2 for 1 mole of O2. So now you have moles of O2. You want to go to CO2, so 2 moles of CO2 for every 3 moles of O2. Okay, then you got moles of CO2. Now go to grams, 44.01 grams CO2 per mole of CO2. And then this one turns out to be 5.43 grams of CO2. Okay, that's the smaller one. This is the smaller amount of the CO2. Therefore, the O2 is the limiting reactant. Okay, good to know. We've got one of the products. Now, you can calculate the amount of water. So this first one is the amount of CO2. Let's go ahead and use the limiting reactant to get the amount of water. So the limiting reactant is the O2. And we could just start all over again here. 5.92 grams of O2 limiting reactant, 32 grams per mole of O2. Then we're going to say 2 moles of H2O for every 3 moles of O2. And then use the molar mass 18.02 grams per mole for water. And this one turns out to be 2.22 grams. So that's the other product. Okay, that's all we have to do. Once we know the limiting reactant, we don't have to do the second calculation. Okay, then we want the amount. So if the limiting reactant is the O2, how much C2H4 is left over? So we're going to calculate the amount consumed, and then we do the subtraction to get the amount that's left over. All right, so we're going to use the limiting reactant again, and we used it here as well. Once you know limiting reactant, you used it to calculate everything else you need. So 4.92 grams of O2, and use your 32 grams per mole of O2. The coefficients here are 3 to 1, so it'll be 1 mole C2H4 is needed to react with 3 moles of O2. And then you have C2H4 moles. You want to go to grams, use 28.08 grams C2H4 per mole C2H4 consumed. So this is going to turn out to be 1.73 grams of C2H4 used up in the reaction. Is that how much that's left over? No. Okay, we started with 1.93 grams. So 1.93 grams C2H4 initial minus 1.73 grams C2H4 used up. And then this is going to be 0.20 grams of C2H4 left over, which is what we want right there. All right, you can do another one of these tables to summarize everything. So let us do that. It's very interesting here. So you have C2H4 plus 3O2 forms 2 CO2s. You don't have to put the coefficients in because we're not focused on that. You can just list them: C2H4, O2, CO2, H2O. So before the reaction, whoops, and then after the reaction, and then we want to look at the total mass. Okay, so we had 1.93 grams of C2H4, 5.92 grams of O2, 0 grams of CO2, and 0 grams of H2O to start with. At the end of the reaction, you have 0.20 grams of C2H4 left over right here. The O2 is the limiting reactant, so it's completely consumed. Then you have 5.43 grams of CO2. That was that first calculation we got. And then the other one was 2.22 grams for the water. And so if you add them up, you get a total of, let's see, my notes are so bad here. I can't read them. 7.85, is that right? Grams. And then 7.85 grams again. All right, now this is interesting. So this is an example of conservation of mass. So you start out with a certain amount, certain mass of your reactants. When the reaction takes place, the sum of the masses, including the leftover, equals the same amount. So no mass has been lost during a chemical reaction. That's the law of conservation of mass. Now later on, next semester, you're going to take nuclear. There'll be a chapter on nuclear chemistry. You're going to learn in a nuclear reaction that some of the mass can be converted to energy. So you get nuclear energy. But in a chemical reaction, it never happens. So there's conservation of mass in a chemical reaction. Not moles, right? We saw that. But for grams, it is absolutely the case. All right, 2 more slides. Yeah, okay, good. Here, this is on the yield. So if you're in the laboratory and you've done an experiment. Sorry, my dog is getting a little excited there. All right, anyway, so in this case, you're in the laboratory, you carry out an experiment, and you weigh out the mass of your products. So that would be considered your actual yield. You want to compare that to the maximum amount of substance that you can make. That's called the theoretical yield. The actual yield from the lab versus what the maximum amount that you could make in theory. You calculate the theoretical yield using the limiting reactant. The ratio of those 2 times 100 is your percent yield. So in your lab notebook, you want to have your actual yield and your percent yield given there. Now the theoretical yield is just like the last example where we calculated how much CO2 can be formed. That's in theory. But in practice, here's the reaction again, C2H4 plus O2 forming CO2. In practice, there can be like a side reaction that could occur. This is a common problem associated with the combustion of these carbon compounds, these hydrocarbons. And so carbon monoxide could be considered as a kind of an impurity in the reaction, formed during the reaction, and it will decrease your yield of CO2. So you might end up with an 80% yield versus a 100% yield if this side reaction were not occurring. Also in the lab, you can spill part of your ingredients. You can have your glassware not clean, and when you weigh by difference to figure out how much you have, maybe there's an error there. I mean, there's all kinds of reasons why you don't get 100% yield. Usually after you calculate your percent yield, you have to analyze and figure out what went wrong. And you don't always know it if there's some side reaction, but sometimes you do. All right, so then we do have this one more limiting reactant problem to look at, and it goes pretty quick. And this is just to illustrate, well, let's read it here. So we have silver and hydrogen sulfide. The phases are not given, but we assume hydrogen sulfide is going to be a gas. So solid silver, gas phase H2S, gas phase O2 is going to form a solid silver sulfide, and then some water as well. So what is the theoretical yield of the silver sulfide if the starting quantities are 0.95 grams of this, 0.14 grams of this, and 0.8 grams of that? So you have three reactants. Which one is the limiting reactant? If you figure out the limiting reactant, then the amount of product can easily be determined from that. Or you could think of that in reverse. Okay, so let's start on a new page here, and we're going to use that book method again. Now we have three reactants, and we have 0.950 grams of silver, 0.140 grams of H2S, and 0.800 grams of O2. So we're going to pick one of the products. Let's look at the silver sulfide because it's asking for the yield of the silver sulfide. Let's do that. Calculate it 3 times in this case. The molar mass of silver, 107.9 grams of silver per mole of silver. Then you have 2-to-4 ratio from the coefficients, 2 moles of silver sulfide for every 4 moles of silver. And then use molar mass of silver sulfide, 247.9 grams. Silver sulfide per mole of silver sulfide. And this turns out to be 1.09 grams of silver sulfide. By the way, let's just go ahead and put the reaction in here. This is 4 silvers, 2 hydrogen sulfides plus O2 forms 2 silver sulfides plus 2 waters. Okay. So next then we're going to take the H2S and use molar mass for that. 34.08 grams H2S per mole. H2S. Then you have 2 moles of silver sulfide for every 2 moles of H2S. Then you have 247.9 grams silver sulfide for every 1 mole of silver sulfide. And this one turns out to be 1.02 grams of silver sulfide formed. The last one is 0.8 grams of O2. Use 32 grams per mole for oxygen. In this case, you got 2 moles silver sulfide for every 1 mole of O2. and use molar mass again, 247.9 grams. Silver sulfide for every 1 mole silver sulfide, and this is 12.4 grams silver sulfide. So the smaller of the 3 masses of silver sulfide is going to be the correct one. That's the correct amount formed in theory. And then that is going to make the H2S here the limiting reactant. We don't need our limiting reactant. We're done with our calculation here, limiting reactant. But anyway, that's how you, just a reminder, that's how you get that. And so then that's how much is formed. This is the theoretical yield. In theory, you could make that much. Now, part B was, what is the percent yield if only 0.62 grams silver sulfide is produced experimentally. So, what is the percent yield? This right here is your actual yield. So you're going to say your actual yield divided by your theoretical yield times 100 will be the percent yield. 61% yield is a reasonable expectation for a laboratory experiment. Of course, we want to get a 99.9% yield. That doesn't happen very often, but sometimes you can get pretty high. On the other hand, you can get very low values, like about a 0.001% yield in the case of biochemical reaction where you got a multi-step process and you're making some natural product. For example, you might get tiny amounts and you go, wow, I got such a great yield, because that's just the way it is. There's a lot of loss, a lot of side reactions that take place for these multi-step problems. Anyway, okay, that's the end of this section, and it's important to work on these examples and other ones on your own. You got to be very comfortable, very kind of quick and fluid with your ability to calculate the amount formed, calculate how much is left over, what the yields are, and so on. So good luck with the homework on that one.